So we're going to begin by discussing some sort of classic problems in accretion disks. So we'll run through some standard arguments that I expect many of you will have seen before if you've been to talks or had discussions on disk physics. And then towards the end, we'll discuss some of the more specific aspects that come up when we think about protoplanetary disks. So if we start with the sort of general questions of disks. The big picture problem, of course, is that we need angular momentum transport to take place if we want material to accrete onto the star. So as we said yesterday, we have an angular velocity which is close to Keplerian, and therefore we have a specific angular momentum, which is just this times r, which goes as r to the 1/2 in a Keplerian flow. So if we have material in a thin accretion disk, we can release energy by moving that material closer to the star and accreting, but moving that material closer to the star is forbidden by angular momentum conservation within the disk. So in the sort of a standard picture of things, there are two somewhat disjoint ways in which we could accomplish the question of accretion. One possibility is that if we have the disk orbiting the star, we could have some turbulent process within the disk which redistributes angular momentum. So we might sort of naively imagine that we have some sort of eddies within the disk that are stirring up the material. They're mixing angular momentum, which will allow angular momentum to move from small scales to large scales while being conserved within the disk flow, while the mass flows inwards towards the star. Okay, so that's one possibility. And then a second possibility, which we've already sort of discussed, would be that we have the disk and we're threading the disk with some net magnetic field. So the magnetic field will have some geometry that looks something like this. And then the idea would be, at least in ideal MHD, that the gas is tied to the field lines, and if these field lines are sufficiently inclined away from the vertical, then the gas can flow out along these field lines, be accelerated, and then as it moves away from the disk, it will remove some of the disk angular momentum, allowing the gas within the disk to flow inwards and be accreted. Okay. So for a very long time, these two sort of pictures were sort of at least typically regarded as being sort of competing hypotheses for what is driving accretion in many astrophysical accretion environments. Okay. What we're going to sort of end up discussing today is how, certainly in the protoplanetary disk case at least, it appears that actually there necessarily has to be some mixture of these processes going on. And the basic argument will be that if we want to stir up turbulence within the disk, we actually need to have some net magnetic field threading the protoplanetary disk. And if we have some net magnetic field threading the disk, then obviously it's quite natural to expect that we might also have outflows along those field lines. Okay. So this is one aspect. This is the angular momentum transport aspect. There's then a second aspect, which is that in protoplanetary disks, it's not necessarily the case that it's angular momentum transport and therefore accretion of gas onto the star that is the main reason, or at least not the only reason, why we're interested in turbulence. So there's then a second aspect, which we'll actually come back to more tomorrow, which one might say is how turbulence may act as a driver of collisions amongst solid particles within the disk. So if we imagine that we have the gas disk and it contains some level of turbulence, even if that turbulence is not actually the main driver of accretion onto the star, then if we have small solid particles which are embedded within the gas, those will be being stirred up by the turbulence, and that can be a driver of the collision velocity between those objects. So we might have a sort of standard circumstance where we have some velocity fluctuations, delta v, which are a function of scale. So that's going to have some scaling with the characteristic size that we're interested in within the disk. And if we imagine perhaps millimeter-sized particles which are trying to collide, on those scales, this coupling to the turbulence may dominate their collision velocity. And if those collision velocities turn out to be too large to permit particles to stick together and accrete, then the turbulence will play a very important role, even if in fact it's negligible from the point of view of driving gas onto the star.
How do you get that scaling?
So this would just be a standard sort of fluid dynamic turbulence scaling. So, as we'll come to on the large scales, what is actually driving the turbulence may be very complicated and not fully understood. But we presumably expect that as we go to sufficiently small scales, we'll just have a regular three-dimensional fluid turbulence situation. Okay, so let's just begin, though, by going through some sort of basic arguments about how we might think about angular momentum transport due to turbulence within disks. So describe this as being the accretion disk analogy for protoplanetary disks. So the simplest situation is to imagine that the disk is axisymmetric, it's thin, and self-gravity is negligible within the flow. Okay, so to make these assumptions, so we have an axisymmetric disk, and it's geometrically thin in the sense that the ratio of the vertical scale height, which we defined yesterday, to the radius is very small compared to unity. And then we assume, in the simplest case, that we have some viscosity within the disk, call that nu, and that the fluid within the disk is non-magnetized and just described by the Navier-Stokes equations. Okay. So in this sort of classical setup, you can just consider the conservation laws for mass and angular momentum and combine them, and you end up with a simple equation for the time evolution of the surface density sigma of the gas in the disk. Okay. That has this form. So it's a simple equation for the time evolution of sigma, and it depends on the radial gradients of the surface density sigma and this viscosity nu. Okay. So what you have here is a diffusion equation for the evolution of sigma under some action of some specified kinematic viscosity. Okay. So this is a well-known solution. So this is diffusion. And if you sort of plot an illustrative solution for this, imagine you have sigma as a function of r, and you start with a delta function of the surface density at some radius, call that r0. So that would represent a thin ring of gas orbiting the star at some particular distance. Then there's an analytic solution for how that ring would evolve in some simple models for what the viscosity might be. So if you say, perhaps you say that the viscosity is a constant as a sort of simple toy model for what would happen. So what happens then is that the material spreads out under the action of the viscosity, and the solution has the form that the material moves closer to the star as time progresses, but then a tail of material moves to larger distances to conserve the overall angular momentum in the flow. Okay, so this is the Lynden-Bell and Pringle similarity Green's function solution for the evolution of a thin ring in a viscous disk. So what you have then is, under the action of viscosity, an initially sharp density structure is smoothed out. The mass flows inwards. A very small amount of mass moves outwards in such a way as to conserve the total angular momentum within the disk. Okay. So if we have this kind of thing going on, there's a characteristic time scale. Call that T nu, which would just be some characteristic scale squared divided by the kinematic viscosity. So if we know something about the viscosity, then given a system of some particular scale, so if we think of a protoplanetary disk, we might be thinking of 10 AU or 100 AU as being the characteristic scale within the disk. We can calculate the time scale on which the viscosity would cause that system to evolve. Okay, so that's all very well. However, the next thing one immediately discovers is that this kind of simple picture for how disks might evolve does not work if the viscosity which enters into this formula is actually the molecular viscosity which is present within the fluid within the disk. And this is true if you're thinking about protoplanetary disks, and it's equally true if you're thinking of disks around compact objects in galactic nuclei and so forth. Okay. So you can do a simple estimate. Let's say that this viscosity is going to be something like the thermal speed within the gas times some mean free path, lambda, and lambda is going to be 1 over n sigma, where n is the number density and sigma is the cross-section for collisions of the molecules within the gas. So you can plug in some numbers here. So let's say that the collision cross-section is something like the physical size of a hydrogen molecule. So that might be, say, pi times 10 to the minus 8 centimeters squared. We already said something yesterday about what sorts of densities we might have within protoplanetary disks. So we'll take n to be 10 to the 15 particles per cubic centimeter. And we said that if we're fairly close to the star, then the thermal speed might be something like a kilometer per second. Okay. So we can plug those numbers in, and then we get something which we actually already mentioned yesterday, that the mean free path is of order centimeters within the disk, so let's say it fairly close to the star, and then the viscosity is something like 10 to the 5 centimeters squared per second. So if you then ask, well, what is the characteristic evolution time for the disk under the action of this molecular viscosity, you end up with a very large number. So this gives you, with these numbers, T nu that's something like 10 to the 13 years. Okay. We said yesterday that from an observational point of view, protoplanetary disks evolve on something like 3 million years, or of order 1 million years, let's say. Okay. So instead, we have a number that's 10 to the 7 times longer than that, and is much longer even than the age of the universe. So this molecular viscosity is negligible from the point of view of causing disk evolution. Okay, so that's not what is going on. And so what do we do? What do we do instead? Well, following the normal sort of development, what you suggest is that there is some effective viscosity that is due to the presence of turbulence within the disk. And in the standard way of writing that, you say that nu is some dimensionless parameter alpha times the sound speed times the disk scale height. And alpha here is described as the Shikuras-Nyaev alpha parameter. And so you can sort of motivate this in various ways based on considerations of turbulence, but for our purposes, we can maybe just think of this as a reparameterization of the viscosity in terms of local properties of the protoplanetary disk. Its temperature, therefore equivalently its sound speed at some distance, and its thickness. Okay. And if you ask how large alpha needs to be in order to reduce that viscous timescale from the 10 to the 13 years you would have from molecular viscosity to more like 1 million years, then you would infer that alpha in protoplanetary disks is maybe of the order of 10 to the minus 2 or 10 to the minus 3. Okay, so it's a number that's smaller than 1, but not vastly smaller than 1. So an alpha of this magnitude leads to a viscous time which is of order of millions of years. Okay. So in thinking about what's going on in protoplanetary disks, what you need is some process that, if you think of turbulence at least, you need some process which will produce an alpha that is sort of in this rough ballpark. Okay? And if you can do that, then you will get something which will cause the disk, the gas within the disk, to evolve on something like the observationally inferred timescales. Now, of course, at this point, you might start becoming concerned that what we derived earlier, the equation I erased a moment ago, the diffusion equation for the surface density, was based on a specific model, Navier-Stokes equations, for how the fluid would evolve. And now we're replacing the actual molecular viscosity, which enters into those equations, with something else, which is the outcome of a turbulent process. So you might wonder whether really a disk that was described by turbulence, driving angular momentum transport, would really behave in the same way as one in which it was really molecular viscosity which was responsible for angular momentum transport. So if you're interested in those questions, which are significant questions, there's work by Balbus and Papalouizou from I think 1999, which actually discusses that question in some detail. And to very briefly sort of summarize the main conclusions, you can consider a turbulent process as giving rise to a similar evolution to one where the angular momentum transport is from a true viscosity, providing that the turbulence is basically locally determined. So providing the amount of stress that you're getting within the disk is determined by the local properties of the flow. And we'll say a little bit more about that when we discuss different mechanisms for turbulence in a minute. Okay, so that's what you have. And then from what I'm going to be saying later, if you have a specific turbulent process in mind, if you can calculate some specific process, you can relate that pretty easily to this alpha parameter, which is sort of often used as let's say, a general order of magnitude way of discussing the efficiency of different processes. Okay? And so the equivalence there is that suppose we have some turbulent disk, perhaps a simulation of a turbulent disk, in which we can measure the fluctuations in the velocity field and the magnetic field within the disk. So we measure some velocity perturbation, dvr, dv phi, in the radial and the azimuthal directions, respectively. And then we divide that by the sound speed squared, and that gives us a dimensionless quantity, which is the contribution to alpha, to the Shakura-Sunyaev alpha parameter, from these turbulent fluctuations when averaged over mass and averaged over time. And then we have a second component, which is magnetic, which depends on the correlation between the radial magnetic field and the azimuthal magnetic field within the disk. So from, if you like, a practical point of view, if we have some hypothesis for what is causing turbulence within a particular disk flow, and we run a simulation of that, we can measure these fluctuating fields. We can calculate the effective alpha and then get an idea of whether that process is really going to transport angular momentum at a rate which would be competitive for explaining what's going on in a disk.
What about the vertical direction?
So here we're interested in radial transport of angular momentum. Okay, so we would, in a sort of practical circumstance, if the turbulence is three-dimensional, we would obviously average over the third dimension, but we don't worry about that third dimension. There could be circumstances, for example, if the disk has a warp, where we would also want to worry about the vertical transport of angular momentum, but that's not what we're considering here. Okay, so that's just descriptions really of what might be going on. Okay, so the basic sort of argument would be if we have turbulence within the disk, if the turbulence is local, it will act something like an effective viscosity with an increased magnitude. And then if we actually know physically what the turbulence is like, we can relate that physical description of the turbulence to what the alpha parameter would be. Okay. But none of this says anything for the moment about really where the turbulence would be coming from. So let's say a little bit about those questions. So where does this turbulence come from? So the first thing we could do would be to ask what sort of characteristic Reynolds numbers would we have if we're considering disk flows. Okay, so we'd write the Reynolds number as being the product of some characteristic velocity, call that capital U, some characteristic scale L, divided by nu. Okay. And if we use for nu here, as we should do, the molecular viscosity within the disk, then the fact that the molecular viscosity is very small, which we already said was an important reason for understanding that molecular viscosity is not what is transporting the angular momentum, that small nu coupled with very large length scales and reasonably large velocity scales will obviously give us a very large value for the Reynolds number. So if we use for this the actual molecular viscosity, then we'll get a very large number, maybe 10 to the 10, 10 to the 11 for the Reynolds number. Okay. So we end up with very, very large numbers for the Reynolds number, which are vastly in excess of what is seen for turbulent flows in terrestrial situations. Okay. However, that doesn't fully solve the problem, because we can also ask, would the rotation profile which we have within the protoplanetary disk be linearly stable or unstable to the development of turbulence? Okay. And so if we just consider hydrodynamic stability, so think about linear stability here, the condition for stability is that the radial gradient of little l, which is the specific angular momentum, needs to be greater than 0 to give us stability. And as we said yesterday and earlier today, because in a protoplanetary disk at least, we have that the disk is vertically thin, the azimuthal velocity profile is very strongly constrained to be very close to Keplerian. So the number we worked out yesterday was something like that the velocity was within 1%, less than 1%, deviating away from the Keplerian value. So the specific angular momentum will be going as r to the 1/2. It will be an increasing function of radius, and therefore it will satisfy this condition for hydrodynamic stability. So we don't have an obvious hydrodynamic route to, if you like, accessing the very large Reynolds number and producing some vigorous turbulence within the disk. Now things are then changed if you have magnetic fields within the disk. And if you're in the regime of ideal MHD, then things are very simple, because the stability condition going from the hydrodynamic limit to the MHD limit just amounts to replacing the specific angular momentum in this formula with the angular velocity within the disk. Okay. So for magnetic fields, the condition would be that the angular velocity, that is the omega squared by dr, would have to be greater than 0 for stability. And in a Keplerian disk, omega goes as r to the minus 3/2. It decreases with distance away from the star. So this condition is not satisfied. Okay. So in a Keplerian flow, you predict that if there are magnetic fields there, and if the fluid is reasonably described by ideal MHD, then you should have instability. Okay, so for Keplerian flow, this MHD consideration predicts instability. And this is described as the magneto-rotational instability. Okay. So if we sort of think in general terms of accretion flows in the universe, in astrophysics, basically at this point we're sort of done. Okay, so we've sort of gone through this chain of argument. Regular molecular viscosity is not enough to explain why we should have angular momentum transport in disks. We need to have some turbulent process which gives us a much larger effective viscosity. Hydrodynamic processes, at least linear hydrodynamic stability, predicts that such disks would be stable against the development of turbulence. But if we place even a weak magnetic field within the disk, we reverse the stability conclusion and find instability. Okay. So for most disks where ideal MHD is a good approximation, we're sort of able to make a conclusion here, right? Even if there was some way to produce some hydrodynamic turbulence completely in the absence of magnetic fields, perhaps through some complicated nonlinear process, or perhaps via some process that taps entropy gradients within the disk rather than the shear directly, very likely that hydrodynamic turbulence would be very subdominant to the turbulence that's produced by magnetic fields. Okay. So in most disk circumstances, the game is then to say, we have this magneto-rotational instability. How efficient is it at producing angular momentum transport? What other observable consequences might it have? How does it perhaps connect into questions of viscous and thermal stability of the flow? Okay. However, things are a little bit different for protoplanetary disks, because for protoplanetary disks, this assumption I'm noted in parentheses here, that this stability condition requires ideal MHD, is very strongly violated. So we talked about yesterday, when we're thinking of protoplanetary disks, we have temperatures that may be as low as 10 degrees Kelvin in the very outermost parts, and are just barely getting above 1,000 Kelvin, even really quite close to the star. So the role of the non-ideal MHD terms is very strongly dominant, and so those may in fact suppress this magneto-rotational instability and change the stability criteria quite substantially. Okay. So for protoplanetary disks, that's then the main concern, or the main issue. So we have sort of two questions. One is, how does the low ionization fraction, write that as Xe, how does that affect things? And then if that low ionization fraction actually manages to either completely suppress the magnetorotational instability or reduce its effectiveness to a very low value, so lower than the observationally inferred values of alpha in these disks. Are there other processes which could generate turbulence which would produce a competitive value of alpha? Okay. So are there other, let's say, purely hydro processes which could give rise to angular momentum transport within these disks? And I would say neither of these questions is really fully understood. Okay? So I'm going to first of all say something about non-MHD processes. Okay? So there are some non-MHD processes which have been identified which can give rise to angular momentum transport in protoplanetary disk environments. And if the MHD processes are sufficiently weak, those could actually be giving rise to the transport which we observe when we see gas accreting onto the star. Okay. So I'll first say a little bit briefly about some of those, or at least just mention what those ideas are. And then I want to say a little bit about the MHD circumstance, but focusing on the role of the non-ideal MHD terms in modifying the magnetorotational instability. Okay, so let's first of all think about the hydrodynamic possibilities. And let's start actually with what might be an important process during the time when protoplanetary disks are actually forming in the first place, and the star is actually accreting the bulk of its mass. Okay. So we said yesterday that many of the disks which we observe, so in particular many of the disks which we see in these beautiful ALMA images, which show rings and so forth, these are relatively isolated disks where most of the gas that was once in a molecular cloud, which formed the star and the disk, has already made it into the star and onto the disk system. Okay. So in those circumstances, actually measuring the disk mass is quite hard, but most inferences of the disk mass are that the disk masses are quite low. So they might be 1/100th of the mass of the central star, or even smaller than that. So as we said yesterday, in that circumstance, the dominant component to gravity within the disk itself is just the components of stellar gravity, obviously the radial component of stellar gravity, and then for the vertical structure, the vertical component of stellar gravity when we're above the disk midplane. However, if we went to an earlier time, that obviously can't be true at very early times. At some point, the star itself must have formed, and during that phase of the evolution, it's very plausible to imagine that the disk was actually quite massive. Okay? You could even imagine perhaps that at some point, most of the mass was in a large rotationally flattened structure, and only a small amount of mass was in the central object. Okay? So the disk could even be more massive than the star. So in that kind of circumstance, the self-gravity of the gas in the disk itself, which we ignored yesterday in thinking about the vertical structure, could be an additional important component for the dynamics. So if we're in this circumstance, we know what the stability criterion is. So if we consider the linear stability, it's controlled by what's described as the Toomere Q parameter, which for a disk that's not extremely massive, so still has basically a Keplerian profile, is just the product of the disk sound speed, the angular velocity, divided by the surface density. Okay, so this is a dimensionless quantity which you can create by basically sort of multiplying together the three things that might control stability. So the sound speed will say something about the role of pressure in resisting self-gravitating disturbances within the disk. Omega will say something about the role of rotation in shearing apart disturbances that are created within the disk. And then the surface density obviously says something about the amount of mass you have present there, and it will be the mass which is obviously driving the gas towards self-gravity. Okay. So fairly clearly, an unstable disk that's unstable to self-gravity will be a massive one, so that would be one with large sigma. So small values of this Q parameter represent the unstable regime. Okay. So if we have instability, that occurs when this tumor Q reaches values that are of the order of unity or smaller. Okay. So you can play around with this a little bit. So if you want to look in the notes, go through the argument. This is a local condition for whether a disk would be unstable to self-gravity, but you can roughly translate, very roughly, translate this into an estimate of the disk mass you need for self-gravity to set in, and very much to be understood in order of magnitude terms. What you require is that the disk mass relative to the stellar mass exceed the thickness of the disk in terms of h over r. Okay. So if we have a disk where h over r is 0.05, which might be a fairly reasonable number, we would need the disk mass to be sort of 5% of the stellar mass for us to have an expectation that self-gravity might be playing a role in the flow. Okay. And as I said yesterday, this condition fulfills a double duty. It's the condition where the self-gravity would affect the vertical structure, so it would obviously tend to compress the disk more than just the vertical component of stellar gravity. But then from this stability criterion, it's also where we would start to develop potentially, well, strictly from this criterion, we'd start to develop axisymmetric rings in the surface density. But when you look at it in a little bit more detail, you find that what actually happens first is that you start to develop spiral arms. So you start to get a structure that resembles a spiral galaxy, though here just in the gas component, where you have spiral arms which develop and ultimately transport angular momentum. Okay, so this may be happening early on. So it may be happening during the star formation phase, when the gas is really falling in at a high rate from the molecular cloud. It's increasing the surface density in the disk, increasing the mass in the disk above this threshold, and then the disk is trying to relax by developing spiral arms, transporting angular momentum, and then the gas flowing in towards the star to be accreted. Okay. So that may be what's going on. I just want to mention there's one other thing you can do based on self-gravity, because if we have a self-gravitating disk, we actually know something about the relationship between the sound speed, which is therefore something about the temperature, and the surface density in the disk. Okay? And that relation, the relationship between those two is basically fixed by the fact that when the disk becomes self-gravitating, we know that the tumor Q is a number of order unity. Okay? And what we see, at least in simulations, is that if you go from a disk where Q is quite large and sort of steadily reduce that value of Q, it's a reasonably sharp onset of spiral arms and efficient angular momentum transport. So if self-gravity is taking place in a disk, we sort of expect that the value of the tumor Q across the disk is going to be pinned fairly close to the threshold value for instability, which, as I say, is of order unity. Okay. So if that's true, and it's obviously not exactly true, but it's true to a pretty reasonable approximation, we can actually do something quite neat, which is that we can actually predict the efficiency of the angular momentum transport, knowing only something about the local thermal properties of the disk. Okay, so I want to just summarize or sketch out that argument. And in the simple case, what we consider is a circumstance where we have a non-irradiated disk. Okay, so going back to yesterday, we said that there were two possible heating processes within disks. One was radiation from the central star, and the other one was dissipation of gravitational potential energy as material is flowing towards the star and being accreted. So for this argument, at least in its simple version, I'm going to neglect the stellar irradiation component. Okay, so I'm going to assume that the disk is just being heated because of the accretion process itself. Okay. So then, in a general viscous disk, you have a heating term which I'm going to write as Q plus, which is 9/4 nu sigma omega squared. And then you have a cooling term, which would be 2 sigma T disk to the 4th. Okay. So I've made some assumptions here, which I'm not going to try to justify in too much detail. So here we're saying that we have an optically thick disk with some photospheric temperature T disk. Disk has two sides, so the cooling rate per unit surface area is just twice the Stefan-Boltzmann constant times the disk temperature to the 4th power. Okay. So this would be the rate at which unit area of the disk will be radiating into space and losing its thermal energy. Okay. Now, if the disk is viscous, and so remember that implies something about locality of angular momentum transport and so forth, then the standard formula for the heating rate due to the viscosity involves the product of the viscosity and the surface density multiplied by the Keplerian angular velocity squared. Okay. So this would be generally true in a viscous disk, but in most disks, knowing these things doesn't really help us to determine what the value of nu is, because here we have one expression that involves the surface density, and then a second expression which involves the temperature, which therefore involves the sound speed. And so if we don't know anything else, those are independent quantities, and saying that the disk is in thermal equilibrium, so that Q plus equals Q minus, doesn't in any way help us to determine nu. Okay. However, if we have a self-gravitating disk, things are a little bit different, because we know that Q is of order unity. And so if we look at that expression on the right-hand board, that pins the relationship between the sound speed and the surface density, where the sound speed should probably be understood basically as being the central sound speed near the midplane of the disk. Okay. So we can then relate that, in principle, to the surface temperature of the disk, and then by assuming thermal equilibrium, that will actually tell us what the angular momentum transport efficiency in the flow is. Okay. So we can play this game for a self-gravitating disk, and so just to sort of sketch out the argument, if we have self-gravity, that tells us a variety of things. It tells us that the tomb rate Q is of order 1. And then if we assume that we're in thermal equilibrium, we can make the assumption that Q plus equals Q minus, and then use that definition of Q to actually determine what nu is and how efficiently angular momentum transport will be taking place within the disk. So, as I've been describing it here, the condition would be that this combination of parameters is, let's say, 2, something like that. Okay. So if I had a particular surface density at some point, it would say that the sound speed needs to be low enough that this Q parameter is, let's say, of order unity.
Okay, I thought that was assuming that we have a self-gravitating disk, and now this is the condition that it's stable.
Sorry. No, so this is the condition that the self-gravity would give rise to a linear instability in the disk. Okay? And roughly, so I've skipped over some things, sorry. So if we imagine we have a certain amount of surface density, okay? If the temperature is too high, then pressure will prevent us from having self-gravitating disturbances, right? And potentially the shear as well, right? And then if you sort of imagine cooling that, this condition will say at what point the self-gravity starts to dominate over the pressure and the shear and give rise ultimately to the spiral arms and the transport.
Have you ever seen those spiral arms? Like, no?
So obviously we've seen them in galaxies, right, where we're dealing mostly with stars. But so we've seen a couple of disks where you do see spiral arms. So I showed one image yesterday, which probably wasn't very clear. There's one system which has been observed with ALMA where we see a nice pair of spiral arms. Okay. Now, I should say it's very uncertain whether those spiral arms are actually caused by self-gravity, because we can actually estimate the mass in that disk, and it does not satisfy the condition for the disk to be unstable. Okay? So we think the disk has too little mass, in fact, to be unstable, and moreover, the spiral arms that we produce, or seen in that disk, are much more open and broad than we would expect given its disk mass. So the situation is that we've seen spiral structure, but it doesn't actually completely match this condition. Now there's another disk which is a much younger system, where we seem to see clearly spiral structure, and we actually see a third star. It's a binary system, and we see a third star appearing to form in that system. So that may actually be the system where we see most clearly self-gravity, and in that circumstance it appears to be giving rise to fragmentation into stars, as well as angular momentum transport.
Why is there no need to consider a direction of the heat flow?
So here we're considering, so if the disk is thin enough, okay, so that would say, in fact, that we're dealing with self-gravity in a regime where h/r is fairly small, then the dominant heating and cooling contributions will be these local radiation and local heating. If we consider an earlier stage where h/r is not so small, then the radial terms would need to be considered as well. Yeah.
So how is Q measured in system?
So say, obviously, if you know the stellar mass at some radius, you'll know omega. You could get at the sound speed by looking just at the brightness of the emission, at least in a simple-minded way. The most difficult thing is going to be to get sigma. Okay? And so the most simple thing you could do would be to measure the intensity of the dust emission and assume some dust-to-gas ratio. You could also measure the intensity of the CO emission, which would tell you something about the mass of gas phase CO, and then try to convert that into a mass of gas phase hydrogen. But all of those processes, or all of those approaches, have quite large uncertainties. Okay, so we're sort of sketching out how this argument works. That the argument works that you say, we know that Q must be of order unity if self-gravity is to be important for transporting angular momentum. We assume that we're in thermal equilibrium, so these heating and cooling processes balance. And then when you do that, what you find is that alpha is something like 1 over omega T cool, where T cool is just defined as U, the total thermal energy content of the disk, divided by the rate at which the disk is radiatively cooling. Okay. So if you have, so you can sort of think of this intuitively, if you're imagining you're at some radius in the disk and the gas is losing energy very rapidly due to radiation, for the disk to stay in thermal equilibrium, it must be generating a corresponding amount of heat. And the only way it can do that is if it's transporting angular momentum efficiently so that gas is falling towards the star and liberating gravitational potential energy. So in this story of self-gravity, there's actually a direct connection between the efficiency of transport and some aspect of the thermal property of the disk, specifically how quickly it can cool. Okay. So what you see here is that as T cool goes down, alpha and the efficiency of angular momentum transport goes up. Okay? And if you think about sort of how this is working in a self-gravitating flow, angular momentum is being transported because one part of the disk is denser than another part of the disk, and it's exerting a gravitational torque on that other part. Okay? So an increasing alpha in a self-gravitating flow implies an increase in the density perturbations that self-gravity is generating, and basically the strength of the spiral arms that are being produced. And so what tends to happen is if you make T cool small enough, and alpha therefore becomes large enough, those perturbations become so strong that actually the gas would collapse into bound objects rather than just simply remaining as spiral arms. Okay. So what is found in simulations is that once alpha exceeds a number that's about 0.1, the disk actually fragments and breaks up into bound structures. Okay, so last night, before we got too taken up in the Japan football game, we were discussing this over beer. This is basically how you get to what I was trying to explain then, how you get to the argument that it's difficult or impossible to form giant planets by fragmentation of gas in protoplanetary disks. Okay, so what you do is you make a model of the disk, you work out where the cooling time would be short enough that the disk would plausibly fragment, and then you ask, in that regime, what sort of mass of fragments would you expect? And what you find when you do that, run through that argument, is that if you're in the circumstance where the cooling time is short enough that the disk would fragment, the surface density is high enough that the fragments would very rapidly accrete and become probably at least low mass stars. So it's difficult to have a protoplanetary disk that is both unstable to fragmentation in a regime where the fragments are the masses that you'd produce for giant planets. So that's basically why we don't think that giant planets can form, at least perhaps, except perhaps in very rare cases, through a process of direct fragmentation under gravity of the disk fluid. Okay, so let's just very briefly say something about other hydrodynamic processes. So I think actually I shall skip over things. Let me just mention that, as we said yesterday, in addition to the radial shear, which is obviously the dominant shear component in disks, there's also a vertical shear. Okay, so if we're at one radius in the disk and we start moving from the midplane to the atmosphere, our angular velocity changes as we go from the midplane to the atmosphere. Okay, so it's possible that that vertical shear can be unstable and give rise to a driver of turbulence. Okay, and so that idea is described as the vertical shear instability, or VSI. It's related to instabilities that were discovered a long time ago in stars. And if you're interested in that, there's work by Richard Nelson and collaborators from 2013, which discusses that process. Okay, it's complicated because it depends also on the thermal properties of the disk, and so how well it would operate would depend on where in the disk you are and how efficiently the disk can cool. Okay. Now, self-gravity, if it's important within disks, is presumably important at an early time when the disk is actually massive. Okay. At later times, we either have to rely on MHD processes or on something like the vertical shear instability to produce transport. Okay. So how does this work? Well, if we go back to the sorts of things that Matt was talking about yesterday, if we're dealing with low ionization environments, the induction equation, the induction equation for the magnetic field has these four different terms. It has one piece that represents ideal MHD, but then it has three additional terms which represent ohmic dissipation, the Hall effect, and ambipolar diffusion. Okay? So what we have here, this is the resistivity, J is the current, so that's just the curl of B. This is the electron number density, and this is the drag coefficient gamma, which represents the ion neutral collision rate. Rho I is the density of ions, rho is the overall density here. Okay? So we have this rather complicated induction equation, and the sort of first thing to note is that these different terms here, even these non-ideal ones, each of them has a different form. Okay? So in particular, they involve different powers of the magnetic field. So the ambipolar term here, the strength of that ambipolar damping depends strongly on the strength of the magnetic field itself. And then they have some different symmetry properties as well. So in particular, the Hall term here is the only one here which depends on the direction of the magnetic field as well as the strength of the magnetic field. So a disk which is threaded by an upwards magnetic field, one in the same direction as the disk rotation, in principle can behave differently from one where the magnetic field is anti-parallel to the disk rotation. Okay. So if we want to ask how this works in protoplanetary disks, how these non-ideal terms modify the magnetorotational instability or give rise to different transport processes or different turbulent processes, there are sort of two parts to the story. One is to ask how would the MRI behave given these terms at the strength that we expect them to be in protoplanetary disks. And then the second question is, can we model the disk structure well enough that we can actually work out what these coefficients that enter these non-ideal terms are accurately enough? Okay, and we said something about that second part yesterday, and maybe correctly convinced you that that's quite a difficult job. Okay, if we want to know basically the ionization fraction, which enters here in various ways through this resistivity, here's this electron number density, here's this ion number density, and this drag coefficient. If we want to work out what these quantities are, we need to know something about the ionization rate, about the recombination rate, sort of ultimately something about the chemistry within the disk. Okay, and that's generally a difficult task. Okay, so we can do some simple things first, though. Okay, so the first thing we can do, which sort of is the historical development of the subject, is to ignore the Hall effect and to ignore ambipolar diffusion. Okay, so we assume that all we have is ideal MHD plus some damping being caused by ohmic diffusion due to the finite conductivity of the disk plasma. Okay, and then you can make actually a very simple timescale argument. You can say if we just had ideal MHD, so we just had this first term, the timescale for the magnetorotational instability to develop would be something like the disk scale height divided by the Alfvén speed. Okay. And the timescale for this ohmic diffusion to damp disturbances in the magnetic field would be something like a characteristic scale squared. We take the vertical thickness to be the scale divided by the magnetic resistivity. Okay. So if we just set those two things equal to one another as an order of magnitude estimate for when this ohmic diffusion would be important at damping the MRI, you get a critical value of the magnetic resistivity, which is just H times VA. And if you then write this magnetic resistivity in terms of the electron fraction, you find a critical electron fraction, which is a very small number. Okay? It's about 10 to the minus 12 or thereabouts. Okay? However, that is larger than either the thermal or the non-thermal ionization fraction that is expected in many models of protoplanetary disks once you're away from the very innermost regions close to the star. Okay? So the argument would be, this is an argument discussed by Charles Gammie in 1996, that this ohmic term, if it was the only thing going on in disks, would act to strongly damp the magnetorotational instability near the midplane of protoplanetary disks, and therefore prevent MHD turbulence from developing in those regions. Okay? Now, in reality, however, you don't just have these two terms, you have all four of them. Okay? And so the other two terms operate in somewhat different ways. So at least in principle, the ambipolar term sort of can operate in a qualitatively similar way to the ohmic term. Okay? So as I've already said, because of these extra powers of the magnetic field, if you like, the diffusion coefficient that's associated with ambipolar damping is nonlinear. It actually depends on the magnetic field itself. However, nonetheless, this ambipolar term can be quite efficient at damping MHD turbulence in regions where the density is low. So notice the density enters basically as 2 powers here on the bottom of this ambipolar term. So if you go to a large distance away from the star, so actually where you're sort of seeing many of those images from ALMA, so those are often looking at disks at 50 or 100 AU scales away from the star, we would expect ambipolar diffusion to be dominant and it to be quite efficient at damping MHD processes. Now there's then finally the Hall term, which is, I would say, it's complicated and different. And if you're interested in that, Matt has a paper from now 10 years ago, which discusses some of the linear physics that's different from the Hall term with respect to these other terms. Okay, but let's say some general things and then quickly show some results from simulations. One thing you can do is you can simply estimate what would be the relative magnitudes of the different non-ideal terms. Okay? And to an order of magnitude level, you can plot that in terms of the density at different places within the disk and the temperature of the disk. Okay? So these different regions here show regions where the different non-ideal terms have different orderings of expected strength. Okay? And these lines show where the midplane of a protoplanetary disk would track as we go from close to the star to large distances, from 1/10 of an AU up to 100 AU, and then this would be in the disk atmosphere where we're up in the Gaussian, and so the density is lower. Okay, so what can we say here? Well, if the temperature was more than about 1,000 Kelvin, we'd be in this regime where the alkali metals are ionized, which we mentioned something about yesterday, and we get a relatively large ionization contribution just coming from collisional processes. Okay? So in this regime, ideal MHD would be a reasonable assumption, and we would expect the magnetorotational instability to be operating. And then there are two other main regions in the disk. If we're, let's say, what we might describe as the inner disk, so sort of 1 to 10 AU scales, so sort of the main area where we would be forming planets, we're in a part of parameter space where the Hall term is strong. Ohmic diffusion is also important, and ambipolar damping is important not in the midplane, but at high distances in the disk atmosphere.
So this Hall term and the ambipolar term, we want turbulence because molecular viscosity is not enough to explain what we see, and so we have to worry about the Hall terms and ambipolar terms because they can damp the MRI instability and we wouldn't have the turbulence needed.
Yes, at least in the way I've developed the argument, that would be the way to think about it. We want turbulence to produce angular momentum transport. The MRI, ideal MHD, would give us turbulence. These other terms, if you like, threaten that. As I'll say in a moment, it's not quite that simple, but yeah. Okay, so we have this inner region where the Hall effect, and then some of the other terms are also important. If we go to the outer disk, so on larger scales, we're at much lower densities, and ambipolar diffusion starts to become the dominant thing that is going on. Okay, so what effects do those terms have? Let me just briefly say something about ambipolar diffusion in the outer disk. In the outer disk, what we think is going on is that the surface layers are reasonably ionized by far ultraviolet flux from the star, and turbulence can be generated in those regions. Okay. In the inner part, even though the density is higher there, the ionization level is sufficiently lower that ambipolar diffusion very strongly damps MHD turbulence. So here's a space-time diagram. This is time on the x-axis. This is height above the midplane. What we're looking here is at magnetic stresses on this color scale, and this sort of gray color indicates a damped region of MHD turbulence, and these red colors indicate some surface activity in the disk, which is being stimulated by external ionization. Okay. Now, what we find is that if you have this damping taking place, you do not obtain large enough accretion rates to flow material into the inner disk if there is no net field threading the disk. So you need some net field, which, as I already mentioned, affects the strength of the ambipolar diffusion because the ambipolar diffusion depends itself on the magnetic field strength. Okay. So we think that this argument suggests that for disks, protoplanetary disks, to be accreting at least two MHD processes, they necessarily have to be threaded by at least a weak external magnetic field, which might be left over from the star formation process. Okay, let me skip through that. What about the inner disk? Well, in the inner disk, things can be quite different. So here's some work from Geoffroy Lesieur, Matt, and Sébastien Froment from a few years back. These are also space-time diagrams. This is height here. And the colors are again representing stress. Okay? But these different panels show different combinations of physics that have been included in local numerical simulations of these disks. Okay? So in this upper panel, we just have ohmic diffusion. Okay? So ohmic diffusion is damping turbulence near the midplane, and then an ionized surface layer is sustaining some turbulence in the disk atmosphere. Okay? So this is rather like that ambipolar plot I showed before. Now, this upper region is actually low density, so if you also include the effect of ambipolar diffusion, that tends to suppress the turbulence in the atmosphere, and the whole system is quite strongly damped. Okay? But when you also have the Hall effect, things are different. You get a laminar magnetic stress, so not really a turbulent stress, which sort of fills the disk midplane and can actually give you quite an efficient rate of mass accretion onto the star. Okay? So this is why I was saying earlier, just briefly, that the Hall term can act in a qualitatively different way from the other two terms. It's not purely a damping process for MHD effects. And then here's some follow-up work from that, where we tried to look at the implied alpha parameter as a function of distance from the star, making some simple assumptions about what the background profile of the disk surface density and the ionization were like. And the main thing that was found there was that depending on whether the magnetic field is aligned or anti-aligned, the net magnetic field is aligned or anti-aligned with the disk rotation, you can either have a solution where you have quite efficient accretion, that's the one that's being shown on those previous slide, or you can have really a solution where things is very strongly damped and there's very little accretion through any process. Okay, so what the magnetic field geometry of these disks is like may make a very large difference to how they accrete. Okay. Now these were all local simulations. So these were little boxes of the disk where the magnetic flux was prescribed at the start and was conserved throughout the simulation. Let me just briefly show a couple of slides from more recent work which relax that and consider global models. This work from Bethune and collaborators. This is a global calculation, also including non-ideal effects. And the main thing to note here that's different is that you can see that the magnetic flux, the net magnetic flux that's threading the disk, develops quite a complicated geometry in these global calculations. Okay, so it doesn't remain nice and uniform and smooth as you go from the inner part of the disk to the outer part. And here's another visualization of this. This is again a space-time diagram, but here you're visualizing magnetic fields. And what you can see is the development of, if you like, stripes of magnetic field, net magnetic field, which are threading the disk at different radii. Okay. So may come back on Friday to say something about this. Yesterday, when we looked at those images of protoplanetary disks with rings, we agreed that planets were one way in which you can produce rings in disks, but here perhaps is a different way in which you could produce rings in disks. Perhaps what's happening is that the magnetic field, which is threading the disk, is self-organizing into a circumstance where you have relatively low density regions threaded by fairly strong magnetic fields, separated by rings of higher density material where the vertical magnetic fields are weaker. Okay. So we'll come back to that, but for now I will stop for today.
Why does the criterion of MRI depend on the value of magnetic field?
Sorry, can you say that again? Why doesn't?
Criterion of magnetic instability doesn't depend on value of magnetic field.
Okay, so the question was, how does the MRI depend on the strength of the magnetic field itself? Okay, and so in ideal MHD, it does depend on the magnetic field strength, but the sort of it's a twofold thing. So if you just consider weak magnetic fields, then changing the magnetic field strength will change the scale on which the system is most unstable. Okay? But in ideal MHD, there's no smallest scale you have to worry about, and so as you go to weaker and weaker magnetic fields, you get different scales, but you always basically get the same maximum growth rate, and that continues until you get a very strong magnetic field, at which point actually then you would wipe out the MRI entirely. Okay? Now that would be for a vertical magnetic field. If you have a toroidal magnetic field, things are a little bit different, and probably the circumstance there is that if you get to magnetic field strengths which are, let's say, larger than the thermal pressure within the disk, significantly larger than the thermal pressure within the disk, you will certainly reduce the MRI growth rates. But then if you go to even stronger magnetic fields, you probably actually get new instabilities developing. So there is a dependence on the magnetic field strength, but in ideal MHD, it's not one that is tremendously important for weak fields, at least.
I didn't catch the sign of the effect. So if B is aligned with the angular momentum of the disk, that enhances the accretion rate, and if they're anti-aligned, it suppresses it.
Yes. So in the limit where the Hall effect is the dominant thing, yeah, it's this sign of the field relative to the rotation axis, and the aligned case is the good case, if you like.
So you're talking a lot about what the gas is doing, the gaseous structure, but how does the solid, how do the solid grains trace that structure?
Right, so the question was, how do the solid material trace the gas structure? So there's sort of various aspects that one might worry about, right? If we think about large-scale features, which might actually be observable, basically the solid material will move towards high-pressure regions in the flow. So if we can create a region that locally is of high pressure, has a pressure maximum, then that will tend to act as a sort of concentrator of solids. Okay. If, on the other hand, we're interested in, if you like, the turbulent coupling to the solids, then what will matter is a parameter that's something like the stopping time of the solids relative to the orbital time of the gas. And generally, if you have very small solids that are very strongly aerodynamically coupled, they will basically follow the gas turbulence quite well. Obviously, very large objects will be completely decoupled, and the strongest effects in terms of, for example, mutual collision velocities will occur at an intermediate regime of marginal coupling. So we'll say a little bit more about that aspect actually tomorrow.